But what I want to do is yesterday we were talking about integrals, and I know everybody got it, and I know everybody understood exactly what I was talking about, but I thought I might take just a few minutes to review, if that's okay. The thing to keep in mind is that when you're given a graph, and a graph is an equation, and you might be given an equation, you might be given the graph, you might be given both, but when you're given the graph for the equation of like position versus time, to find the velocity at any time, you take the derivative. And we practice that, and I think you guys are fairly comfortable with taking the derivative. If I give you the graph of velocity versus time, or the equation of velocity versus time, you can go back and derive the position versus time information by taking the integral or calculating the area underneath the curve. And if the curve is really nice and has straight linear lines, you can use squares, rectangles, triangles, and literally calculate the area, and everything works out really swell. But if it's not, if the curve, we got a velocity versus time curve that looks something like that, it's not as clear cut. That's not a straight line, by the way. That's actually a very poorly drawn line. It's not as clear cut. And so what we have to do is divide the area underneath the curve. Let's say that's time is 0, and let's say this is 5 seconds. We're interested in this part of the curve. And what we want to do is divide up that area into little rectangles, calculate the actual area of each rectangle, and then add up all the little areas. And that's what we achieve through the integration process. Now, let me redraw this on a large scale. So this is 5 seconds. And it's still a velocity versus time graph. And so I'm going to pick that point right there. And what I'm going to do is I'm going to basically break this up into a little bit of a rectangle. One side of my rectangle might go a little bit above the curve, one's a little bit below, but you know, I'm not going to worry too much about that for these purposes. Now, if this equation, let's say the equation I tried to draw right was the velocity is equal to t squared. It's roughly that equation, which is roughly that graph. Then the height of my rectangle is just simply t squared. And the width is a very small increment in time. And the very small increment in time is dt. And so the area of this little rectangle is simply time squared times dt, height times width. Okay? That's a little area. I'm interested in overall, like an area, this whole shaded in area. And so all I calculated was a little bit of the area. A little bit of the area is denoted as dA. That d means a little bit, for lack of anything better to say. And so I'm going to do the same thing, maybe right here. I'm going to calculate the area. And once again, it's the same expression. The width is dt, the height is t squared, so the area is t squared times dt. It is everywhere. But we're just going to integrate, and we're going to add up all these little areas, like the summation. And when we do the summation, but what we're going to end up doing is adding up all these little dAs. We're going to have that rectangle, the rectangle that's right here, the rectangle that's right here, the rectangle that's right here. We're going to add up all these little rectangles, and we do that through the summation or through the integral process. We use the summation, you're familiar with that, the sigma, if we have specific numbers. 1 plus 2 plus 3 plus 4 plus 5. We don't have specific numbers. We have very small numbers. And so when we're dealing with very small numbers, we don't do the summation, but we do what's called the integral. And the integral is just the opposite of the derivative. Because what we're going to do is we're going to get a curve, we're going to get an equation where if we take the derivative of that equation, we're going to get t squared. And that's how they're related. And so we're going to take a look at the mechanics of the integral. I just kind of showed it to you on the PowerPoint yesterday really fast, and you just really freaked out. Oh my God, I'm never going to be able to understand that. It's not that bad. So what I want to do is I want to take the integral, I want to add up all these little areas. And so when we add them up, we're taking the integral. Here's my area. And I'm going to go from x is equal to 0 to 5. Whoops. That's the whole plan. Now, what this means right here, what this dt means is I'm only interested in the expressions with t in it. Oh, I only have the t squared, so that's okay. And so we got to look at this and say, we want the antiderivative. What equation with t in it, when we take the derivative, gives us simply t squared? Well, I know that this squared has to go to a 3. I'm going backwards. So I know I'm going to end up with something t raised to the 3rd. Right? If I took the derivative of t cubed, what do we get? 3t squared. Well, I don't have a 3 in front of here. So that must mean I need a 1/3 right there. So that when I bring this 3 down, the 3 times 1/3, they cancel each other out. And this is, there might be a better thought process. Well, I'm sure there's a better thought process. This is mine. Because I'm just working it backwards. And I'm going to focus first on what is the power. In my integral, it's 2. I know it has to raise to 3. Then when I take the derivative and I bring this 3 down, 3 times something gives me 1. Well, 3 times a 3rd gives me 1. So this is part of my answer. The other part is I actually have to evaluate what this expression means. And I'm going to evaluate it from 0 to 5, meaning I'm going to plug 5 in for t minus 0 plugged in for t. And then whatever that number is, that's my area underneath the curve. So if my velocity function is equal to t squared, and the question is, how far does it go in the first 5 seconds? velocity is how fast it goes. But I want to know how far it goes. That means we got to integrate it. We got to go from velocity to position. So my position with respect to time is the integral of my velocity. Because all I'm doing is really integrating my velocity equation with respect to time. This is graphically what I'm doing. This is mathematically what I'm doing. So I'm going to take my velocity function with respect to time. I'm only interested in the first 5 seconds, so I'm going from 0 to 5. So I want to know how far it goes. Take my antiderivative of t squared, that's 1/3 t cubed, and I'm going to evaluate it between 0 and 5, which means I'm going to take 1/3 5 cubit minus 1/3 0 cubit. Now, once you get in the hang of it, you should be able to recognize that 0 plugged in there is nothing. So this is saying the 1/3 times 0 is a little redundant, but I wanted to show you where it went. If this was a 1, I'd put a 1 in here. If it was a 2, I'd put a 2 in here. Let's see, 5 cubed is, thank you, 41.2. So if my velocity function is t squared, in the first 5 seconds, it's going to go 41.2 meters. That's all this is telling me. That's when I want to find out the specific value. Now, how's that? Is that okay?